Welcome back to Geometry. We're at section 12.1, dealing with tangent lines. If you need to hit the pause button, go ahead and fill out the following definitions. I'm going to go ahead and start. All right, the first new term we have is called a tangent line. Now, we recall from trigonometry that we use sine, we use cosine, and we use tangent. Well, in this case, tangent lines are not referring to trigonometry or SOHCAHTOA or any of that stuff. It's actually a new term, and here's what happens. We have a line that's in space that's going to be drawn, and this line in space that's drawn is going to come and touch and intersect the circle in one point on the outside and then keep going on forever. Okay, and when a line that only hits a circle in one point on the outside occurs, that's called a tangent line. Okay, so we can say that this line that's drawn is a tangent line to the circle. Then we also have what's called a point of tangency. So if we put a point at our center of the circle and then draw a radius, I'm getting a little bit ahead of myself. Let's go back to this point right here. So we have this line that's called a tangent line, and it's going to hit the circle in one point. Where this tangent line hits the circle in one point is called a point of tangency. Okay, so this point right here is our point of tangency. Then what happens when we draw in our radius is that it's always going to be perpendicular to the tangent line. So we can put 90-degree angles here and here. And so that's what our theorem says, is that the tangent line and the radius drawn must be perpendicular at the point of tangency. And so that's what we've shown here. It's also true that if we use its converse, that if a radius is perpendicular to a line on the circle, then the line must be a tangent line. Alright, so those are our two new terms. We're going to work with those and solve these problems. First problem, we're said that TJ is tangent to circle O at T. The first thing you should do is put a 90-degree box at angle T. What allows us to do that is we're told that TJ is tangent, so we need to put that box there. And we can actually do that on every single problem. So segment TJ is going to be tangent for all of these problems, so we're going to put a 90-degree box there. Alright, that helps us solve. So next we're told that TJ is 12, our base. We're told that TO is 9. TO is a radius. OK is also a radius. Alright, so we're trying to find the entire length, or just the length of KJ, which for right now we can call X. Okay, so we're trying to find this length. Well, there's a few ways that we can solve. I think the easiest way is to take a squared plus b squared is equal to c squared. And we end up getting 15 is equal to c. And if this whole length is equal to 15 and 9 is used up by the radius, that means jk, or this segment length kj, or x, has to be 6. Next we have measure angle TOJ is 60 degrees. That means with this 90 I can put 30 degrees here. We're told that TO is 10, so OK is going to be 10. Those are both radii. And we're asked to find the length of KJ again, which would be this amount here. Alright, we're going to use the rules of a 30, 60, 90 triangle. If we look at our short leg, which is opposite our 30-degree side, we see 10. So opposite our 60-degree side would be 10 rad 3. And then to move from short leg over to hypotenuse, we would multiply by 20. And if this whole length is 20, that means x has to be 10. Next, we're told that TO is 5. That means OK is 5 as well. Those are both radii. We're told the whole length of JO is 8, which makes this piece 3. And we're trying to find TJ. I guess let's call it X for unknown. So in this problem, we're going to take 5 squared a squared plus b squared x squared equals 8 squared. X squared is equal to 64 minus 25, so x squared equals 39. So we get rad 39 is equal to x. Alright, next problem. If x is 117 degrees, find measured angle CBA. So again, on problem 2, we should have been told that BC and BA are tangent. We would need to be told that these lines are tangent. For some reason, it wasn't told that to you in your notes, but it should have been. So since they're tangent, the first thing we should do is put 90 degree angles here and here. Next, x is 117 degrees. And so if we're asked to find measured angle CBA, that's this known angle here. Well, we can do that. One other thing to note too is that these two sides are both congruent because they're both radii. And since these two angles are the same, what we have here is a kite. And we know that in a kite or in any quadrilateral, we have 360 degrees. We're going to add up 117, 90, and 90. And when we do that, we get 297. So that means angle B has to be a 63 degree angle. Alright, 3, DE is tangent at point D. Put a 90 degree box here. If this angle is 38, we know that x has to be 52 degrees. There's 180 degrees in all triangles. Alright, 4, this is a challenging problem. We have a belt fits tightly around 2 pulleys. They want you to find the distance between the center of the 2 pulleys. So let's draw that line in. Okay, so we're trying to find x. Let's go and call it x. And what we want to do here is use the other information that's given and then solve. So what I want to do here is I'm going to draw a line that's parallel to xy. Okay, and if I do that, and it's parallel to xy, then what I know is, since these two lines are both parallel, this angle here and this angle here are corresponding angles. Furthermore, what we have now created, I can move this 90 degree here, is that we have a rectangle. So this length is going to be 15. Alright, and then if I know that these two sides are the same, these two sides are the same as well, this radius is 3, so this radius is 3, which makes this side of the rectangle 3 as well. And if this radius is 7, that means this piece is going to be 4. So I'm going to redraw this triangle. I'm going to change colors to show you what I'm going to do. I'm going to redraw this right triangle, and the reason why is I'm trying to find x, which is opposite our 90 degree angle, so it's going to be our hypotenuse. So sorry about that, let's change back colors. Okay, so here comes our triangle. Here's our 90 degree angle. Point P is not our 90 degree angle, so P is going to be down at the base. Y is going to be up on top. And where I created this new rectangle, let's call this point, let's just call it T. Okay, so here's point T. Alright, so it looks like the length from P to T is 4, so there's my base. It looks like the length from, alright, Y, where is point, oh sorry, this is not point Y, this should be point O. There we go. This is point O. So from point O to P is x. X is going to stay there unknown. And from O to T, we have 15. So to find x, we're going to take a squared plus b squared equals c squared. 16 plus 225 equals x squared. And so x equals 241 square root sine. Alright, next theorem, we have theorem 12.3. Two segments that are tangent to the same circle from a point outside the circle must be congruent. Alright, what we're what we're saying here is that we have these two lines. Okay, so we're given that AB and BC are tangent to circle O. Okay, and what we're going to try and prove is that BA is congruent equal to BC. So we're trying to prove this theorem 12.3. So anytime we do a proof, usually we like to do a two-column proof. So we're going to start off with our statement reasons. One, we're going to draw a line here that's given. All right, from there, let's make some marks. I'm going to draw in a radius from O to where this point's at, A. And I'm going to draw in a second radius from O to C. All right, and since these are both radii, they're both congruent. That's going to be statement number 2. Is I'm going to say that AO is congruent equal to CO, and that's because all radii are congruent. All right, next, since AB and BC are tangent, let's put a 90-degree box here and a 90-degree box here. So I'm going to say, let's go, let's do this first. We're going to say that OA is perpendicular to BA, comma. OC is perpendicular to BC. And that's because that's definition of a tangent line and slash point of tangency. Okay, so what we're saying is that since BA and BC are tangent at their points of tangency on the circle with a radius drawn, we know that it creates 90-degree angles, and that's what we said here by saying that they are perpendicular. Let's also say that angle A is congruent equal to angle C, and that's because all right angles are congruent. All right, next we're going to draw in segment BO, and by reflexive property we can say that BO is congruent equal to itself. So we're going to continue our proof. Statement 5, we're going to say that BO is congruent equal to BO, and that's by the reflexive property. And so if we think about how we prove that two triangles are congruent, right now you might be thinking SSA, which we're not allowed to use SSA because it spells a bad word backwards, but we are allowed to use the HL theorem. So the HL theorem says we need a hypotenuse and leg and two right triangles. We have that. Here's our hypotenuse and here's our leg. So we're going to say that these two triangles, let's call it triangle BOA, is congruent equal to triangle BOC, and that's by the HL theorem. Alright, and if these two triangles are each congruent, then what we can now say is that BA is congruent equal to BC by CPCTC. Since these two triangles are each congruent, we now know that these two lengths have to be the same as well by CPCTC. Alright, next, we're going to use that last theorem that we just learned. So the whole key here is that on these problems, all of these lines that are tangent start from the same point X. And so as a result, since all these lines are from the same point X and they're tangent, then it means that all these lengths are the same. So if AX is 5, BX is 5, CX is 5, and DX is 5. And so that was from the theorem on our previous page, which said theorem 12.3, which says that if lines that are tangent start from the same point, their lengths will always be the same. So that's what we have here. We can say that dx is 5. Alright, they want us to find the perimeter of the entire triangle. Again, since these are points of tangency, then this length is 10, this length also has to be 10. Then if this length is 15, this length also has to be 15. And then if this length is 8, that means EC has to be 8. And so we add all those up, and we would get 66 centimeters for the perimeter. All right, we're going to do the same thing here. If we know this piece is 1.3, this piece is 1.3, clearly this shape is not drawn to scale. And so if this is 1.3 and the total is 3.4, that means this piece is 2.1. This piece is also 2.1. And then if this piece is 3.6, this piece has to be 1.5. This piece has to be 1.5. And then if we have 5.7, this piece has to be 4.2, and this piece has to be 4.2. And we add all those up, and we get 17.8 inches is our perimeter. Alright, next we say that a polygon is inscribed. Let's spell this right. There we go. Inscribed in a circle when all vertices, corners are on the circle. In this case, we can also say that the circle is circumscribed about the polygon. Alright, so here's what's going on. They want us to draw a circle inscribed in a square. So how I think of it is when they ask you to inscribe something, the word in means inside. So you're going to draw a circle inside a square, and that's inscribed. Okay, so this is a circle inscribed a square. Alright, circumscribed about means that we're going to go outside. So if we have let's just keep our shapes the same. We can do a pentagon, but I'm going to keep it the same as a square, just like last problem. And this time the circle goes on the outside. Okay, and so that would be circumscribed. Alright, down to the algebra review. We're actually going to do these problems in class, so thanks for joining us. See you next time.